My observation is that there's a delay between me and most of you. Okay. Every time I touch a key, it takes a while before it changes. Okay. So you've got that. That's it now. It's certainly working now anyway, yeah. Right, well, let's see how we get on. I'll recap. This gentleman in 1835, given the experience of science and exploration and various other things in chemistry and physics until that time, he'd come to the conclusion that we'd never know what goes on in stars. And so he'd given up on the whole thing. And yet this was the foremost French philosopher of science at the time. In fact, probably he invented the term philosophy of science. And his conclusion would have left science in a gap. You know, it just wouldn't have progressed at all. And yet we know it has. And that's because, can you see that? The title? Yep, that's it, it's showing, yeah. Okay, fine. All we've got to go on is the light that we get from these things we call stars. And the ultimate story of this talk, if we ever get to the end of it, is about the study of spectra, or the light coming from them. It's all we've got to go on. And that's all we will ever get from the stars themselves. How do we know anything about light before we start dissecting the light from stars? Well, what do we know about what's here on Earth? We know about the sun, which provides heat and light together. But historically, nobody seemed to connect the two, as we'll see shortly. And moonlight, which is reflected light. So there's no heat from the moon, but there is light. Now we understand that the sun is emitting both, but the moon is only reflecting it. What about heat and light on Earth? We've got heat and light in a fire. Anything that is combustible and glows emits light. Are they the same things? So, but we are apt to be fooled by nature sometimes, as in this picture here. This is an appearance and reality problem. We know about this and we think we know why it happens, but we also have one of these. It's a very distinct optical phenomenon, but you try to go find the bottom of it and you will find it rather difficult. So what is really going on down here? Can we really look at stars and believe that they're real? Why isn't it just a canopy of bright light hanging above the Earth sufficiently far away that we can't get at them? It might be fooling us all the time. Anyway, what we know about the material universe has come via this light from above. And it is limited in the sense that at first, the only aspect of it that we could divine anything from it was through eyesight. So the big question for this evening really is, what does light or radiation have to tell us about matter? How are the two things connected when they seem so different from each other? Mr. Newton had a few thoughts about this, which we'll touch on later on. And he said, and I'll quote, from his Optics, this is 1717, the second edition, the text is the same in his original. Are not gross bodies, meaning bodies with mass, and light convertible one into the other? And may not bodies receive as much of their activity from the particles of light which enter their composition? The changing of bodies into light and light into bodies is conformal to the course of nature, which seems delighted with transmutations. So he felt that light and matter were made of the same sort of things and were interchangeable. Now that's quite foresighted. Possibly, I suspect he didn't, well, had he understood the modern view of light and particles and so on, he may have not come to that conclusion. I think this is more in his imagination than anything else. So what about heavenly light? We've seen what we've got on Earth, we've got the experience of it, we've measured it, we've played around with it and so on. Well, you all know about this, the daily and annual cycles of celestial events and so on, and it's been a fascinating thing for millennia upon millennia. And despite their limited resources, astronomical observers from many, many years past have built this picture of the sky and made these arbitrary, largely arbitrary structures that we all see in the sky here. And you're all familiar with this, of course. I'm going to look particularly at one part of it down there, a form of a few stars that look very familiar, the Orion group. Naked eye observation of that group has noted the fact that here, in the top left-hand corner, this star is quite bright, but it's reddish in color. And the bottom diagonal on the right, Rigel, is bluish in color. Now, why should that be? Up here, Aldebaran up in Taurus and Alcyone up in the Pleiades are each red and bluish as well. So why would they be reddish and bluish? Now, it's obviously to do with their temperatures. There's a picture that will show them in actual. I think this may be a Hubble picture. Can't remember now because the presentation's a bit old. And we now know that a star's color is determined by its surface temperature. And here you can see that a bluish star is a hot star at about 11,000 K, whereas Betelgeuse, a huge star, is cooler at 3,500 K. And here's a few indications of the relative sizes here. Jupiter's orbit is only 1¼ times the size of Betelgeuse, whereas Rigel is much, much smaller. And Jupiter's orbit is 14 times the size of Rigel. So it's small, very bright and hot and blue. And so we've got this difference, or this range of colors from red to blue, but there are no green ones. And we'll find out why that is shortly. So here's another question to ponder throughout the evening. How do we know the temperature of stars? How do we know that Rigel is approximately 11,000 Kelvin? Let's go back a few steps. The original ancient observers, and more recent ones to some extent, used to think that the heavens were perfect, comprised of concentric celestial spheres whose rotation accounted for the apparent motions of the fixed and the wandering stars or planets. The Dutch spectacle maker Hans Lippershey patented a refracting telescope in 1608, and I've put patented in quotes there because it only applied in Holland, and there wasn't a patenting system as we know it at that time anyway. He just got a kind of license from his local government to have a bit of a monopoly over the making of these things. And the observations that were made using this device, both in Holland and elsewhere, which we'll come to shortly, led to the realization that celestial objects are very far from ideal. Now, I'm sure you'll be aware that the invention of the telescope is a very long and complex and contested history. On the bottom of the screen, there's a link there, which I'll give you again at the end if you want to go and have a look at that history. But this is where it starts, in effect. And Galileo is the one who's credited with recording the first details of the moon's surface and those of some planets and their moons. And he published his findings in his famous book, Sidereus Nuncius, on January 30th in 1610, using a telescope like this one. It's a meter long, 25mm aperture, and a magnification of only 20 times. And by the way, the lenses at each end, one here and one here, didn't work particularly well, but they worked well enough for him to observe that these objects out there were far from the ideals that they had previously been considered to be. Now, of course, we've made massive strides since then. We've seen some wonderful images from Hubble in the optical, and hopefully by the summer or the autumn, we'll have some infrared pictures from this wonderful device that's made it out there into space to L2, Lagrange 2. And this man here, Christian Huygens, is the beginning of the story of how we've seriously tried to understand light as light rather than some phenomenon that we just take for granted every day. Had it not been for Newton, he would probably been accepted as the most famous and able astronomer and scientist of his age. He was influenced by people who came before him, of course, like Galileo, we just mentioned, but he was also, his family at least, were very friendly with Leibniz and Descartes. So he had the great benefit of learning from these people and thinking about what he'd been told mathematically by Leibniz and Descartes' ideas of vortices and so on that explained the workings of the cosmos. He influenced Newton for sure, and became an FRS in 1663, thanks to his influence on British scientists like Newton. He met Newton in 1689, and it's said that he went to Cambridge to meet Newton and travelled back to London in a coach with him. And in those days, of course, that would have taken quite a while. I would have liked to have been a fly on the coach wall and hear that conversation. But one of the things he did was to anticipate Newton in applying mathematics to explain and to codify natural phenomena, like light in particular. By the way, he made an improved pendulum clock. A pendulum clock was invented to some extent by Galileo in 1656, and it was used to try and determine longitude, which was a big navigational problem back in the 17th century. And the Royal Navy actually tested one of his pendulum clocks in 1664, despite the fact that Holland, at that point, Holland and Britain were engaged in one of their several trade wars. And his contribution to observation and to optics in general was the invention of the so-called Higgins eyepiece here, which shows two pieces of glass, convex, plano-convex in two of them, with these particular distances relating them. In other words, the focal length of this one, the focal length of that one, and the two items are separated by a distance of the sum of those two focal lengths divided by 2. And it improved the quality of his telescope considerably. And of course, he used that to find Saturn's rings and explain the ring system and so on, which you probably know about. He's particularly noticed for his theory of gravity. He wrote in French mostly. Pesanteur is the French word for gravity, but in particular for this evening's interest, his wave theory of light, published in 1678. That was enhanced by Thomas Young in 1802. He finding the double slit experiment, which proved that light was more of a wave than what Newton had thought, and that is a corpuscular theory of light. The thing was developed further by Fresnel in France in 1816, and ultimately by Maxwell in 1864, who produced the Maxwell equations, which very strongly supported the idea of light as a wave. And I said he studied Saturn and discovered its moon in 1665 and so on. And we've honored the man by calling an ESA probe that landed on Titan in 2005. There's a mountain on the moon, a Martian crater, and an asteroid, number 2801. Very important man on the way to understanding light. Now, the man who really put many things on the map, including light, was, of course, Isaac Newton. We all know about his Principia, theory of gravity, but he also had a corpuscular theory of light. But he did, if you read the document carefully, he did consider the idea that light was what he called ethereal undulations, in other words, waves. He didn't quite know, he never came to understand it. However, the thing he's most famous for, and what we're talking about principally this evening, is a spectrum. He reports in his optics these experiments with prisms and the way that light, white light, or sunlight in his case, breaks up into the well-known pattern. However, as I'll come to later, he misses certain things about this spectrum. One of them is that he didn't see the gaps in them, which we'll see later. And he didn't notice that there is heat associated with the sun. If you remember when I started, we talked about earthly light being accompanied by heat from the sun. Well, surely heat was coming through that prism, but he couldn't see it, and he didn't explore it any further. However, his other claim to fame, of course, is his observations and his use of a reflecting telescope, primarily to avoid the aberrations, the chromatic and spherical aberrations caused by lenses of the time, although people like Dollond did improve, as I've told you Higgins did, in trying to get to the aberrations under control. And Newton became an FRS in 1672, largely on the strength of his gravity is Principia rather than anything else. And now a prism and a telescope, these two things combined together are the two essential parts of a spectroscope, a thing that analyzes the spectrum in more detail than just observing the phenomenon itself. Now, somebody who did take an interest in more than light, stimulated presumably by Newton, was William Herschel. Now, you'll all know about William Herschel because he was well known among astronomers. He also happened to be a fine musician, but that's not our interest this evening. But what he did do was look at heat. At the time, no link was known to exist between heat and light. They were two separate phenomena, despite the fact that sunlight exhibited both. Now, what Herschel did, and here down on the left, you have a prism with sunlight coming into it, refracted down onto a set of thermometers down here. So he wasn't interested in the light, it was the heat. So he put thermometers in the different parts of the colors of the spectrum and realized that the temperatures were different in each part of the band. He came to the conclusion that there was a phenomenon from the sun which he called radiant heat. Now, this sounds very simplistic to us because we're familiar with it, but it wasn't familiar at the time. He realized that effectively that on the invisible part of the spectrum, there was a thing we now call infrared. Now, when he published his results in March 1800 to the Royal Society, that report went around Europe, and a chap called Johann Ritter in Germany went down the other end, and he explored the ultraviolet part using chemistry, which is much more difficult, of course, but he realized also there was radiation on either side of the optical, which made people more and more curious about the nature of sunlight in particular. This is what Herschel said. I'll let you read it. I'll just pick out the main words. He says, if we call light the things that illuminate objects and heat, radiant heat, that which heat them, it may be inquired whether light be essentially different from radiant heat. The answer to which I would suggest that we are not allowed by the rules of philosophizing to admit two different causes to explain these effects than when they can be accounted for by one. It's kind of Occam's razor in effect. But what he's saying is, surely these things should be the similar phenomena and not be treated differently. Now we can leap ahead quite a bit now, having discovered through Newton that light is made up of parts, different colors, and that either side of that optical visible spectrum, there is both ultraviolet activity and heat on the other end. By this time, lots of people, including specifically this gentleman, Fraunhofer, in Germany, who was looking much more carefully and was recording what he was seeing much more carefully, such that in 1814, he published a text and discovered that the spectrum wasn't smooth and continuous the way that Newton had illustrated, because he'd missed these gaps. It's actually full of gaps, the Fraunhofer lines. This is an image. This here is taken from his publication, and it was treated as a great step forward in terms of scientific interest, at least, even to the extent that in a centenary in 1887, the German Post Office actually published a stamp that recorded this directly from his text onto the stamp, showing what we'll come to shortly as the effectively absorption spectrum of sunlight, complete with its gaps. Now, he used prisms, just as Newton had, but he also used finely scored glass, a grating, in other words, as is used in most modern instruments to provide much, much better resolution than some prisms can do. So Fraunhofer starts to look at these and speculate as to why this is the case. Why are we seeing these dark lines? if you haven't seen them for yourselves, all you have to do is look at a CD or something like that, because the fine structure of the pits cut into the surface of the plastic act exactly like a grating, and shows these color fringes as you turn it in the light. Further on into the century after that, these two gentlemen, Bunsen you will have heard of, Krochhoff you may have heard of, they were working together at Heidelberg, and they effectively produced for the time, a very accurate spectrometer. And you see that here in the picture on the left. The prism is in the middle here, a hot burning specimen in Mr. Bunsen's burner here, a telescope to collimate the light, pass it through the prism, and a telescope to view it at the other end. And you can change the angles of the telescopes at either end so that you can look at the different light as it different wavelengths of the light as it emerges from the prism here. He was a chemist. Bunsen was a chemist. He wanted to know, well, he was using light and the spectra to try and understand the chemistry of the object that was burning here or heated here. Krochhoff was more of a physicist. And between them, they produced this spectrometer. It was much more precise and accurate than anything that had been produced so far. And they introduced the idea of using multiple prisms here to bend the light even further and stretch it so you can see in more and more detail the lines that Fraunhofer had discovered some while before. And so effectively, these guys kick off the science of spectroscopy by making a precision instrument, for the time at least. And one of the things they managed to prove was that the emission spectrum, in other words, the light emitted by something that's burning here, and the absorption lines that Fraunhofer had discovered, the things with the black lines in, actually corresponded, which Armstrong had discovered some while before, but hadn't been able to prove. By the way, Krochhoff also did many other things. For example, he's got some electric circuit theory rules, but in particular, for our interest, he studied what's called black body radiation. And if you kind of cast your minds back to my two questions towards the beginning of this evening's talk, we are trying to understand the relationship between radiation, light, and heat to some extent, and matter, solid objects, matter. Now, this black body radiation is fundamental to that understanding. Now, one of Bunsen's former students, somebody called Henry Enfield Roscoe, brought this work from Germany back to England and brought it to the attention of the Royal Society. And soon, Mr. Roscoe was offering spectroscopy lectures to the public. Here's the front page of a book of 6 lectures he delivered, which was published by Macmillan's in 1878. After one such presentation to the Chemical Society, remember that Bunsen was a chemist, and some of this work was done to explore the chemistry of the of materials rather than anything else. The moderator of the session said, as a result of that presentation, if we were to go to the sun and to bring away some portions of it and analyze them in our laboratories, we could not examine them more accurately than we can by this new mode of spectrum analysis. Now, we've immediately got to the point here in 1860 to confound Mr. Auguste Comte's views of 1835 that we can never ever do that. However, what really excited the moderator, Mr. Leroux, was the potential that this method of analysis of light portended for astronomy, and of course, how right he was. Here's a photograph of the two German scientists again, Mr. Roscoe, Mr. Krochhoff, and Mr. Bunsen. And this was taken in Manchester in 1862. So there was obviously a great deal of collaboration going on within Europe and in particular between England and Germany. A point of sort of passing interest that this gentleman, Roscoe, was an uncle to Beatrix Potter, the well-known children's story author. So what about these spectra? The work up until this point by Bunsen and Krochhoff and others had managed to discover that there were several types of spectrum. This is the one, the continuous spectrum is the one that Newton would recognize. It's the separation of white light. And here we must be careful what we mean by white. White in scientific or physical terms is an ideal light. It has equal intensity at all wavelengths, but that's not what human vision would see if you gave it a set of wavelengths. The human eye, the human visual system is very complex in that sense. Newton used sunlight, which is yellowish, but Newton's light produces naturally a continuous spectrum with no gaps and no emphases in it, simply by passing plain white light through a glass prism which deflects the light. The red light, of course, deflects less than the blue light. Now, an emission spectrum is not quite the same as that. This white light, this multi-wavelength light, is not quite the same as a hot gas. A hot gas is made of elements, groups of elements and compounds and so on. And if it is heated up and its light is passed through a prism, this is what you get. You do not get a full range of continuous spectrum. You simply get the light lines, specific wavelengths that are unique to whatever the elements in this hot gas are. That's an emission spectrum. An absorption spectrum is the inverse of that. You take your white light again, but this time pass it through a cool gas. It may be the same gas as we used before, but a cool gas this time, is you can't quite see it because it's not glowing. However, the white light from here passes through it and then comes to this prism to be broken up in this way, in which case you do get much of the spectrum from the white light, but holes in it where the gas has absorbed the energy at these specific wavelengths. And Krochhoff and Bunsen's discovery was that the bright emission light here is exactly corresponding to the dark absorption light here. Now, in this shown up here, you can, as I said in the case of Krochhoff and Bunsen, if you want to see more detail in any of this, you have to stretch the spectrum, and that's why multiple prisms were used to achieve that. Here's some typical spectra. Hydrogen, relatively simple, but rich in the ultraviolet. Helium, also rich in the UV, but with this very strong yellow line, which we'll meet again shortly. And neon and sodium and mercury, you can see they all have these unique spectra, in which case, if you were given some light without knowing like where it came from, and if, say, it was sodium, you would clearly see these two yellow bright lines and this one in the cyan here. The fluorescent tube doesn't quite work the same way as an emission spectrum, but nevertheless, it looks like white light because of the stimulation of the emission of the material inside the tube. Now, these are elemental, pure spectra, but of course in nature, they will be composites, including a mixture of the various elements that are in the source. And even hydrogen emissions, although it looks relatively simple up here, goes well beyond the limits of optical light. You can induce a hydrogen atom to emit in the UV and in X-rays as well. This gentleman is probably Britain's initial serious attempt at astronomy. This is Joseph Lockyer. He became interested in spectroscopy as an analytical tool. And he discovered a line, a very prominent emission line at 588 nanometers in sunlight. He suggested that it was called by some unknown at the time, solar element, which he called helium. So we met helium just now, and this is the gentleman who discovered and named it. Now, in 1882, 20 or so years later, an Italian scientist called Palmieri isolated the gas in eruptions from Vesuvius, in which case this is not just an element in the sun, it is also an element observable on Earth. On the strength of this and other work, he became the world's first professor of astronomical physics in London, now part of Imperial College, and an observatory was built for him as its director, and he directed it until he retired in 1913. Now having retired, he built his own observatory near Sidmouth in Devon, and he became the founder and the first editor of the well-known scientific journal Nature. This observatory is visitable down in Sidmouth if you fancy a trip from up there in Scotland. This gentleman is equally important in the evolution of spectroscopy and its use in astronomy, but hardly ever known outside of limited circles. William Huggins. In 1885, 25 years after Kirchhoff's report of 1860 on his spectroscopy work, this lady, Agnes Mary Clark, who was a historian of astronomy, there's a book she wrote published in 1885 which summarized the state of the art at that time. She said, spectroscopy promises everything. It has already performed much. It will doubtless perform much more. However, she identified the enterprising British astronomer William Huggins here, not Kirchhoff, not Roscoe or Lockyer, as one of stellar spectroscopy's principal founders. He wasn't originally meant to be an astronomer. He was meant to be running the family drapery business, but he was sent off to Cambridge. But while he was up there, he developed a strong amateur interest in astronomy and spectroscopy. He managed to keep these two things going. He ran the company in London, but at home in South London, he built an observatory where he and his wife, not unlike Herschel and his sister Caroline, were doing extensive observations of spectral emission lines and absorption lines of various celestial objects. In other words, stars or anything you could observe through a telescope. This lady's work is this book here, which you can still get, not as a book necessarily, but there is a version online. Now, Mr. Huggins started taking photographs, or at least dry plate images of various objects in the sky. And in August 1864, he took the spectrum of a planetary nebula when he had a look at NGC 6543, the famous Cat's Eye Nebula. He was also the first to distinguish the spectra of nebulae and galaxies by showing some, like the Orion Nebula, had a pure emission spectra characteristic of gas, whilst the Andromeda galaxy had the spectral characteristics of stars. Now, I put Lockyer in brackets, exclamation mark here, because Lockyer furiously disagreed with him. He thought that he did not agree that nebulae and galaxies were two different astronomical objects. Mr. Huggins, as I mentioned, started using photography to record the spectra from these various observations, and his analysis of the spectra was greatly assisted by the fact that he happened to live next door to William Allen Miller, who was a professor of chemistry at King's College. So between them, they were able to identify the chemistry through the spectra of the light that Huggins was observing. And in 1864, the two published papers, they published two papers reporting their observations of the light of Aldebaran, finding sodium, magnesium, hydrogen, calcium, iron, bismuth, tellurium, this is antimony, and mercury, among other things. So he also, in 1868, reported observations of Sirius, and he noticed that it exhibited a redshift. Now, redshift had been predicted as a Doppler effect by Fizeau, the famous French physicist, in 1848. But now we have Huggins actually observing the fact that there was a redshift. Its actual redshift is something like 5.5 kilometers per second, which isn't particularly fast, but nevertheless, it exists and was demonstrated by Mr. Huggins. If you want to know more about this work, which is well worth a read, there is a book published by the CUP called Unraveling Starlight, and it describes the work of William Huggins. Time moves on, and more people get interested, not so much in astronomy, but particularly in spectroscopy, and the power it has to tell us more about the nature of the stars we observe in the night sky. This gentleman, or I should say, Father Secchi of Society of Jesus, was the director of the Pontifical Gregorian University in Rome and was one of the first scientists to claim that the sun was a star. He studied here in the UK, also with the US Navy. Now, what on earth the US Navy were doing studying, taking on Jesuit priests to study, I don't know, but it might be something worth following up on, and obtained a Doctor of Divinity at Georgetown University. But he was a pioneer of astronomical spectroscopy. He showed that the absorption of the Earth's atmosphere affected the observed spectrum of the sun, for example, and recorded the fact. And from about 1863, he accumulated well over 4,000 stellar spectrograms, discovering that stars form a limited number of distinct types, distinguished by their spectra. Now, from this concept, he developed the first system of stellar classification, the so-called 5 Secchi classes. Well, this is quite limited compared to what we know today, but in doing all this work, he discovered carbon stars, for example, which is one of his spectral classes, through a recognition of molecular bands of carbon radicals, which tells you that the quality and the instrumentation and the observational skills of these people to discover molecules, including carbon radicals, is well advanced. A carbon star is one that's run out of its oxygen effectively, and it's made it all into carbon monoxide. And because carbon monoxide is extremely stable, it requires 11 electron volts to dissociate it. It means it's abundant because of its longevity in the universe. So there's plenty of it out there in the interstellar medium, which is there to be detected through, for example, absorption spectra. And although he was a pioneer, and which is a fundamental of classification, which is a fundamental element of astrophysics, his system clearly was in need of extension, and it was done by the Harvard Observatory people. By 1900, great strides had been made in linking chemistry and astronomy, and identifying known materials not only in emitting objects like stars or nebulae, but something about the materials that would emitting that light. And from 1882, Edward Pickering directed the observatory and developed the Henry Draper stellar classification system. The minute analysis of photographic plates was done by a group of women called the Harvard Computers. And this eventually led by enhancement to the well-known and quite famous now Hertzsprung-Russell diagram. This is Henry Draper. This lady, Antonia Maury, was one of the earliest of the Harvard Computers. She happened to be the niece of Henry Draper, so got involved in the family business, as it were. And the study of the spectra of the bright northern stars was a major part of her work, contribution to classifications. But of course, this work broadened, and we have Antonia here, a lady called Williamina Fleming, and Henrietta Swan Leavitt, and Annie Jump Cannon, famous women who contributed significantly to spectral analysis and classification. You may be interested to know that Williamina Fleming, née Stevens, was born in Dundee and had gone with her husband of the time to the USA. They separated, but she managed to find work with Pickering, it's a stroke of luck, who recognized her talent and attention to detail and brought her into his group of Harvard Computers. And in 1923, a lady called Cecilia Payne, who was extremely important in the future of astronomy and astrophysics, joined the group from Cambridge, where she couldn't get a degree, and came to Harvard and obtained the first astronomy doctorate by a woman in 1925. Here are all the ladies. This is Williamina from Dundee. This is Henrietta Swan Leavitt, and this is Annie Jump Cannon, all famous in their time. Now, by 1925, the only ones left were Antonia, sat here, Annie Jump Cannon here, and Cecilia Payne there. Sadly, Williamina and Henrietta had both died by this point, but had contributed very significantly to the idea of spectral classifications. But given that we've learned an awful lot about spectra, where do they actually physically come from? We observe them, we've analyzed them, we've identified them with stars and nebulae and galaxies and so on, but we still don't really understand how matter can produce the phenomenon of spectrum. By combining all the observations to date, this gentleman, Mr. Balmer, in 1885, discovered that there were structures in the absorption and emission lines that we've observed, we've learned about earlier on. And he found a set of connected lines which turned out to be, which would eventually call the Balmer lines after him. Soon afterwards, a Swedish physicist by the name of Rydberg found an empirical formula that matched these lines. In other words, he could account for these lines that Balmer had discovered using this formula down here. The wavelengths in vacuum with Rydberg's constant and a couple of integers here in this pattern. We're not going to go into that, just to report the fact that we were learning about the structure of spectra by looking at the relationships between the observed lines. That prompted more work. So by 1906, we have an American professor, Lyman, who found a series that also fitted in with Rydberg's formula. Another gentleman by the name of Ritz discovered that if you had the sum and difference of two lines in the existing sets, they also fell into this formula. And it was subsequently learned by several people, Plackett, Fund and Humphreys, for example, yet more lines that fell into this formula here with the Rydberg constant. Why would that be? Why should we know about this? Well, by the time we get to 1900, we knew that Rydberg's formula worked, and we could predict where these, or from a spectrum, we could work out what was present in it, or what was emitting it or absorbing it. What we didn't know was a theoretical explanation for it. Why is matter doing this? And in 1900, nobody knew why stars were hot or how they generated light at all. And it took another 30 odd years before people like Rutherford, Einstein, Eddington, and so on were able to contribute to the answer, to explain all of that. The path to the answer was found in 1900 when Planck presented a solution to the famous black body problem, the nature of the radiation emitted, observed on Earth and elsewhere, by a body that is hot. This was Planck's quantum theory, which revolutionized physics and led to the idea of the photon, particulate light. So we've come around full circle. We spent most of the century after Huygens' idea that light was a wave, and Maxwell kind of producing a mathematical background to that in 1860s. But now Einstein comes along as a result of reading about the quantum theory, comes up with a photoelectric effect explanation for which he gets his Nobel Prize in well, the paper was published in 1905. He didn't get his Nobel until 1919. But this is the birth of quantum theory, which is the thing that tells us how spectra actually get generated. The observations that led to Planck's solution is shown in this diagram here. if you plot the energy density in the light coming from a hot body and measure it accurately wavelength by wavelength and plot the result, this is what you get. So for a body at 3000 Kelvin is here, its peak wavelength is around about a nanometer, but heat it up to 4000 Kelvin and its peak is now just about in the red, the optical visible red, human eyesight visible red. Raise it another 1000 degrees to 5000 Kelvin and you get a broad spectrum that's the whole of which is now visible. So you've got red light through green light and down to blue light, all present at the same time. So a body at 5000 K looks white because your eye is seeing all of the colors it's able to see and interprets that as white light. It isn't white physically because it's not constant, but a body at 5000 K looks like that. And a hot sun, for example, is very close to that temperature. The surface temperature of the sun is not far off 5000 K. This explains why there can't be any green stars. As a body gets hotter and hotter, the first light is red. Gradually it gets redder and redder, and then the green element is present but not visible as green. It becomes a yellow light, and then gradually it gets hotter and hotter, introducing blue light, and the hotter still, even more, and the whole thing will shift away from the visible. So if you get a body hot enough, you won't be able to see it by the naked eye, at least, because its peak radiation has gone way out of the band that your eye can see. Oh, a classical explanation for this wasn't discovered. In fact, the classical prediction was this black line here. For a 5000 Kelvin body, this is what it should look like. According to the theory of the time, the theories of Krochhoff that failed, Wien, who we'll come to shortly again, Lord Rayleigh, James Jeans, all of them had a go at it and could not match the reality that is shown in these diagrams with a prediction. The failure is particularly bad between the prediction, the classical prediction, and the reality, and it's called the ultraviolet catastrophe. Note this curve that joins the peaks of these particular temperature curves here. It's important. So when Planck revealed an exact solution that actually did meet all these curves correctly, he had to use his quantum theory. He introduced his quantum theory. He did it in exasperation. He didn't like the result. He never did, almost till his dying day. He accepted it, that it worked, but he didn't like it. Basically, he was a classicist in terms of science, physics, but and he didn't realize the consequences of what he'd done. And yet, what he had produced was an exact prediction of the reality, the observed reality of hot body radiation. Now, it's interesting. Don't go into this too closely. Just note one thing, that the two variables of importance are the temperature of the object and the wavelength distribution of the light that comes from it, and that they two things are related through that expression, which is made up of these universal constants: pi, Planck's constant, the speed of light, Euler's number, roughly 2.718, and the Boltzmann constant. Now, it shouldn't be a surprise that the Boltzmann constant is evolved because it's to do with heat, thermodynamics, and so on. Now, Mr. Wien, which we've mentioned, had a go at solving this and failed. But what he did discover was his famous law. Now, what you've seen in this isn't so obvious in this diagram, but if you plot this exact same diagram as a log, in other words, take the logarithm of the wavelength, the logarithm of the energy density, and plot it again, this is what you get. And if you look at the peaks, they all line up in a straight line, which means that Mr. Wien's law is that if you multiply the peak wavelength, the wavelength at which the maximum energy density exists in the light from an object, a hot object, times its temperature, is a constant. Now, if you project this all the way down to low temperature of 2.7 K, you can now say what the cosmic background radiation spectrum should look like. Here you've got the visible spectrum, and this dotted line is the so-called Draper line, or the Draper temperature, Henry Draper, that we talked about before. You notice that as something gets hotter and hotter, it starts emitting in the red, and it only becomes visible round about the Draper point when it's roughly 800 K, when the red light is just about visible. And as it gets hotter and hotter, more and more of that light is emitted in the optical, the visible. These are the various hot objects we know about out there. Is the sun, Sirius rather, at something just under 10,000 Kelvin, very bright white blue star. The sun is here, Betelgeuse here, lower temperatures. This is the last scattering surface, which is what the universe was supposed to be at the point at which recombination happened and light was released into the cosmos. And that's what we look at effectively when we see the cosmic background. And the Earth is way down here at roughly 300 Kelvin. A massive million, 6 orders of magnitude difference between the peak spectrum, the wavelength of the peak energy, to that of, say, Betelgeuse. Very important law. But how does this actually relate to materials? We still haven't got there. We've got a much better grasp of why things look the way they are and why they are hot. Now, the 1913 or 12, roughly 1913, Niels Bohr published his idea, developed from Rutherford's model of the atom, that the electrons are only allowed to orbit, and I put orbit in quotes here because they're not strictly orbits in the planetary sense. They are states that the electrons can be in. And this is an image of a hydrogen atom, the simplest, a proton and a single electron revolving around it in some fashion. All other atoms, of course, are derivatives of this by packing in more electrons and more protons. Now, if you allow, I don't know what's going on here, I'm not touching anything and it's moving on. As the electrons are changing orbits, if they get an injection of energy, they're allowed to climb the energy ladder by absorbing it or emitting it when they fall down the energy ladder. So when the electrons are moving between orbits, they may emit light or they may absorb light. So we're getting somewhere now to understand the relationship between the physical material object, or matter made of atoms, and the light that they may absorb or emit. This was given an extra theoretical basis when Louis de Broglie produced his ideas in the middle 20s, that not only has light got a wave characteristic, but matter itself has, the electrons themselves have. And that led eventually to the electron microscope, of course, but a much shorter wavelength to see things in much more detail. And his wavelengths, he calculated, agreed exactly with Bohr's model. Now, this work inspired Schrödinger's famous equation. We're not going to go into that in detail, just to note that we have finally got to a point where we can understand the relationship between light as it is emitted from matter in the form of atoms or groups of atoms and combinations of atoms to what we observe in those spectra that we saw earlier on. The Balmer series, for example, is now explicable because what we now find from observation is these series of lines can now be related to the energy states of the electrons in the atoms of the emitters or absorbers, and to the shell levels, Bohr's idea of shell levels, numbers n and 1, 2, 3, 4, and so on. These ones are the ones we see more likely. these are the ones that are up in the X-ray region, which we'll never see, but these are the Lyman series, and Passion series are down in the infrared, and we won't see those either. These are the ones we do see. And this particular spectrum, this particular series, the lower Balmer series involving shells 2, 3, and so on, are these. And this is exactly the spectrum that hydrogen emits, that is visible. Now these lines can be split. If you apply them an electric field to a series of atoms or a gas, these lines remain more or less as they are, but they split into pairs. And if you do the same thing with the magnetic field, the famous Zeeman effect, it also splits the light. But we understand that by doing the right experiments, and once we've got the basis of the physics, we can predict and observe and learn. And in particular, we can learn about magnetic fields and electric fields out there in the interstellar medium simply by looking at spectra and to see whether these splits exist in the spectrum as we observe it. This problem of relating the precise nature of the electrons moving between their objects was still slightly woolly until Heisenberg comes along and in his quantum mechanics, Planck's quantum mechanics ideas are applied to the hydrogen atom in particular. He could not predict from what was already known about the atom to these precise wavelengths here, but Heisenberg came up with a solution and gets his Nobel Prize as a result. So we've more or less completed the link between a spectrum and the emissions of and light and the properties of matter through the atomic, the behavior of atoms as we understood it. But this projects on into astronomical spectroscopy. Now we know now we have the instruments, now we know that have the physics and the science, we can now observe, astronomically observe and learn more about the objects out there than we could have before. And the famous result is Vesto-Slipher using the spectrum as a means of measuring redshifts. So he scans the skies with these telescopes down in Arizona and comes up with a publication in 1914, which met with great success and inspired a young Hubble in the audience who carried this work on. And his course is well known, his work is well known. The Hubble constant, the famous Hubble constant, was derived from his observations of distant objects using ladders, of course, using standard candles and so on to estimate the distance, and the redshifts from the spectra will tell him what the recession rates are to give the value of the redshift. And of course, he was able then to plot the linear relationship between the two. And of course, Hubble didn't do all the work himself. Most of the actual recording work was done by Milton Humason. If you want to know more about his personal recollections of his work working for Hubble, there is an American Institute of Physics interview transcript available at this address. If you're interested, I'll give it to you later at the end or by email afterwards or something. Effectively, what Hubble and Humason discovered was the fact that the greater the redshift, the further away the signal was, the object was, and there is a linear relationship between the two. Now, there's argument these days about the precise value of the Hubble constant, depending on how you go about measuring it, but nevertheless, this relationship seems to hold. Improving observations of spectra and light in general. If you've got an extremely weak, as Hubble did, of course, go back here, some of these things are a huge distance away and extremely faint. How do you evaluate light when it's so faint? Well, there comes a point where photographic recording and the properties of the optics of a telescope get in the way of that. So what happened was a man called Ken Tward developed a thermionic multiphoton multiplier tube, which has a lot in common with early television camera tubes made in the 30s, 40s, and 50s. And he was then able to amplify weak signals coming from very distant objects and give the ability to analyze the light and its spectrum. Now, subsequent to that, of course, nowadays we're using semiconductor devices, charge coupled devices in particular, which makes this thermionic machine here, which is quite bulky and big, makes them relatively obsolete. Again, the ARP, the American Institute of Physics, has a copy of some of Kent Ford's personal recollections, which they've transcribed, and there's a document you could download if you're interested to hear about that. And astronomically, the significance of Kent Ford's contribution is through the work of Vera Rubin, who used his spectroscope at various observatories to discover effectively, or not so much discover it, but suspect that something is not fully explicable in revolving galaxies. And effectively, it's a discovery of dark matter, confirming the ideas of Franz Vicky that goes way back into the 1930s. So spectrum, again, significant in these observations and the deductions from them. 2 or 3 final slides now. Here's some actual spectra, or images rather, taken from the Sloan Digital Sky Survey, 3 of them. This is M105, Herschel 304, and M84. They all look much the same. Their spectral classes are different, but as you can see, this one looks a little whiter than this one, looks more yellow. And if you look at those objects and look at the spectra, but more to the point, also look at the redshifts as well, this is what you see. So what looks to be 3 very similar objects are 3 quite different ones, because here you've got the red here means a receding or redshift measure of the material in this halo here, and in the top left corner of the halo, it's blue shifting. That tells you it's revolving. This bit's coming towards us, that's going away from us. This one is very similar, a much smaller, more compact object, but again, you can see the redshift on the right and the blue shift on the left. But this one, the NGC 4374, it looks like some kind of cluster with objects moving in all sorts of directions, with a rough idea of the outer part is moving away and the inner part is perhaps coming towards, but it's a mixed bag of observations, which is rather peculiar. But the spectra and the redshift combined tells us something about the movement or the motion of these things. Very bright stars, if they're revolving, I mean, I've taken the example here of Vega and Altair, 2 of the somewhat triangle stars. The observation of Altair, which is the blue one, shows no peak at the hydrogen line, 656 nanometers, is a very sharp hydrogen line coming out of Vega, which suggests that it's not moving very much and it's not revolving very much. Yet Altair's smeared. And the explanation for that is it's revolving. And the detail is over here on the left. That's indicative of the way that spectra, or the particular lines in the hydrogen line, in this case spectrum, can tell you something about the nature of the motion of the object. Supernova shells, if you look at the shell of the emissions from the supernova explosion, look in particular at the silicon-2 line, which should be 635.5 nanometers. It isn't. It measures at 615. So that's a blue shift of 0.032 or 3.2% the speed of light. So the shell, the outer shell of this, is coming towards us at some phenomenal rate, 22 million miles an hour, which is phenomenal. all learned because of the redshift and the spectrum. Quasars, here's light from 3C273, a quasar at a huge distance away. Nevertheless, we can judge from the redshift and the spectrum lines using this one, H alpha 656 nanometers, again, shifted significantly down to 760, tells us something about the recession rate, and using the Hubble constant, we can determine the distance. We can even do it with meteors passing quickly through the sky. If we can observe them, we can determine their compositions. 3 types of meteor exist: iron-based metal ones, or stony iron ones, a mixture, and some mostly silicates. And the different types of meteors, the Perseids and the Geminids, have got this spectral fingerprint attached to them. And some of this work can be done these days with some relatively modest equipment. This spectrum was taken from an attachment to a telescope shown here. Now, all we've looked at so far is the optical spectrum. And we've learned a huge amount about the makeup of the universe and the behavior of stars and nebulae and so on, all mostly to do with light here, in this section here. What we haven't done and are doing from orbit is looking at X-ray spectra, ultraviolet spectra, gamma ray spectrums, and of course radio astronomy is basically spectroscopy, but using radio waves. So there's a huge amount of more work can be done in spectroscopy using these different technologies. Here's some books you might be interested in. 3 of them, I've got a list I can send up to you of all these 3 books. These are kind of professional ones, if you see what I mean. These are written by physicists mostly, but these 3 books are things you can do with more modest resources, things you can attach to your home domestic telescopes. And that is an insight to some of the secrets of Starlight. Thank you for your attention. Sorry about the mix-up earlier on.
No problem.
And sorry it's taken a bit too long as well. It's all that loss of time at the beginning didn't help.
Do you want to, can you close your screen share, please?
Yeah, I'm trying to, I'll find it. There we go.
Please.
Oh, you want me to stop?
Yes.
Yeah, sorry.
Do you want me to stop sharing, or did you ask me to reshare?
Well, it's that, yeah, unless you're going to use it again, if you could stop
No,
it.
no.
Then we get the gallery view, we can all see each other.
Sorry. No.
That was excellent.
Yeah,
I thought I knew a lot about spectroscopy anyway, you know, because I was a physicist, but I learned quite a lot there. Thank you very much. Not me.
If you would like some of the details of all those references, I've got it written down in a Word document, which I can send up to someone. Perhaps Alice Amanda's the best.
Aye, that'd be great. Aye.
I'll send it up to you, and whoever wants it can then get it from you.
Yes, that'd be brilliant.
Okay.
Yeah.
Any questions or clarifications or what?
I mean, that was
I'm
really
very sorry,
interesting.
I have no idea what all that mix up at the beginning was all about.
No, it was very comprehensive.
It was.
Yeah, enjoyed it. Thank you.
Yeah, I hadn't realised that Fraunhofer had died so young.
Yeah,
You know,
well, yes, Huygens did as well. It seemed that yes, what is it? Favors the brave or something. There's a saying about people being taken before their time.
Aye, because Fraunhofer seemingly had died a heavy metal poisoning from the vapours from making the glass.
Well, yes, it's a bit like Hatter's, you know, the Mad Hatter's syndrome.
Aye.
Mercury, it's an industrial hazard.
Aye. Yeah.
But they didn't know, of course, and the Curies exposing themselves to radioactivity without really.
I know.
Mm.
I know.
But without these people Well, they weren't taking risks really, were they? Because they didn't know they were taking risks. They
No,
were
that's true.
doing things. Yes.
I mean, it took me back to my science degree with OU. all the stuff that, you know, the Balmer lines, the Lyman,
Yes.
you know, and the Pashan.
Yeah.
I'm like,
Yeah.
oh, I did all that stuff. I used to have to calculate everything for the TMAs and that.
Yes. Well, Fraunhofer in Germany is, in scientific circles, is extremely well known. There's a Fraunhofer Institute, a research institute.
Right.
And I forget where it is. It's somewhere like Munich, I think. But it's branched out away from things like spectrum and light. They actually own the algorithm that runs your MP3 player.
All right. Good.
Lockyer is a really major setback. Really, I think it has an effect on him. It makes him doubt, I think, inwardly his ability to lead Germany. The physical and mental stress on him is absolutely immense. He has insomnia, he finds it difficult to sleep. He doesn't quite know what to do.
For once, there is no master plan.
Sorry, Kenny, I think we're listening to your telly.
Oh, yes, I thought it was a bit strange.
I was beginning to wonder what was going on.
No, I didn't think Fraunhofer had left Germany.
No. I'm thinking, what's going on?
Yes.
Very strange.
It was very strange.
Anyway, he's gone now.
But one of the other interesting things about this, the development of this science over the last couple of hundred years, is how much of it was done in Britain and in Germany. Not many, I mean, not a great number of French scientists mentioned at all. Fizeau was involved in the early days in his famous experiment to measure the speed of light and so on. But nobody else seemed to be too much involved in it, which is interesting.
Of course, a lot of the work on the atom was done by Rutherford, wasn't it, as well?
That's right, yes, in Canada to start with, and then Manchester and Cambridge, of course. That's another talk I've given down here in Bristol in the past, is nuclear synthesis, which is clearly relevant to the processes going on in stars. And I've mentioned that there are big red stars like Betelgeuse, and very bright hot ones like Rigel, and us, the sun in the middle. Well, our sun can't get as far as Rigel because it'll never be hot enough because it's too small. Only a very, very massive star can generate the gravity that collapses it to produce the temperatures that burn the nuclear synthesis process to make bigger and bigger and bigger and heavier atoms.
Yep. Because I recently, Mike Frost for the BAA had mentioned about Paul Dirac's book, The Strangest Man. So I recently purchased that. So I'll be reading that in the summer.
It's a good read. And of course, it's highly relevant to me here in Bristol because that's where he was born and bred, effectively. And did an engineering degree here in the university before going on to Cambridge, where he did his best work, I suppose. And in fact, in the city, it's one of the bugbears that we have a grumble about here. Down by what passes for a science museum down in the city centre near the harbour, there is this pointy thing. It's a kind of coloured pointy cone thing without anything on it. And it's supposed to be a monument to Dirac.
Right.
But people just walk past it. I mean, a clue what it is. There is a blue plaque on the house he lived in, but that's as much as the city has done to recognise the great Paul Dirac.
I mean, what's the point you think supposed to represent?
Well, I don't know. We occasionally have occasion to go past it and have a look at it and just wonder again, what on earth has he got to do with anything? It's not symbolic at all. I'd like to put his statue on the plinth that had Colston. You remember that somebody pulled Colston's, the slave trader guy, pulled his statue down.
Aye.
Well, put Dirac up there. He's done some extremely great things for the world of physics.
Aye.
Bristol should be proud, but it doesn't. It probably hasn't a clue. If you took 100 people in the streets of Bristol and asked,
Aye, they wouldn't have a clue who he was.
they wouldn't know who he was. Yeah.
No. No, I think he's only famous within the physics and astronomy community. I don't think nobody else seems to really know who he is,
Yeah.
which is a shame.
Yes, well, I'm sure you'll enjoy the book.
Oh, I definitely I will. Yeah.
The strangest man. He must have been on the spectrum, as they say, because his gifts don't come without a cost.
Aye.
He wasn't a particularly sociable person. He didn't have an lot to say for himself. Famous stories about him giving a lecture and then waiting for questions, and somebody in the audience just said something, and he didn't respond. So the chairman of the session said, more or less, "Did you hear that question, Professor Dirac?" And he said, "It wasn't a question." You know, these people's minds sometimes are extremely logical.
Yeah.
Because I've got loads of Richard Feynman books, and I've read quite a few Richard Feynman stuff as well. So I really like
He's
Feynman.
another interesting character, totally
Aye.
different from Dirac, of course, but in quite the opposite in his social behaviour.
Aye, the character, you know, it was such a, his book and that, surely you must be joking, Mr.
That's the one,
Feynman.
yes.
Oh
That's a good
God, it
introduction.
was such a hoot. You know,
Yes.
the things he got up to in that, smoking pot and different
That's
things.
right, yes.
You know,
He worked at Oak Ridge in the Manhattan Project. He worked at Oak Ridge and was, like other scientists, he was very upset by the military system of need to know.
aye.
So all he did was pick the locks.
I know, because in the book it talked about how when you know, he would go into the other offices, his colleagues, and pick their safes.
Yes, that's right.
And then we just up and then we on, "Oh, you've been in here." Oh yes, of course.
Well, he and the other scientists working there, of course, were used to an open discussion environment to try and, you know, bounce ideas around. And yet the military discipline wanted it to be hermetically sealed. So people couldn't communicate, which is not really what you wanted. There we are. There we are.
Because it gave me a good, it was a good laugh, the book, you know, it was serious, but it was a good laugh. It was such a, I just thought it was absolutely brilliant. Because the first book I had of his was The Character of Physical Law, because I had
I had
to read that, well, bits of that book for Matter in the Universe course. It was an astronomy course I did with the OU, and that was one of the books that we had to purchase, you know, for that. So it was, and that book got me hooked on Feynman.
Good.
But so I like Einstein as well, right enough. But that got loads of Einstein books and all. All right. So is there any other questions for Gordon?
No.
Right. Thank you so much for your informative and interesting talk. As I'm sure I can speak for everyone else that we've all learned something new that we didn't know before, or at least we knew a bit about, but not well enough. and you've expanded on the detail. It's a very comprehensive talk, and it brought back a lot of my modules I did with the Open University in my science degree, particularly the astronomy and some of the physics stuff. So I'd like us to thank Gordon in the usual Kaz way.
Thank you all very much. Once again, apologies for the hiccuping start. It's you can't rely on the technology, can you?
Indeed,
No.
it's always a problem.
No, I mean it wouldn't be a Kaz meeting if there wasn't a technical issue. I mean, even when we met physically, face to face, there was usually some technical hiccup.
Yeah.
Well, as I said, it's the first time I've had a problem like that. Every other time I've used Zoom, it's worked perfectly well. So
Right.
goodness knows what happened this time.
No.
Because when Professor Ian Morrison came one time to give them the memorial lecture, we'd huddle round about his laptop because the digital projector bulb had went.
Ah, right.
Yeah.
So, I mean, thankfully it went not really great, but there was only like 6 of us there, which wasn't really a great amount, but it wasn't a great night anyway, the weather-wise. But, I mean, he didn't bother, he didn't bat an eyelid, he just he carried on, and we just sort of, we just huddled round his laptop. And I think the same thing happened with Alan Walker. Remember, we had to just like go around each lap. There was different laptops, and when Alan Walker did his talk, and we had to we'd ought to link the laptops up, and we had to watch his talk on there.
Mm.